So today I'm going to be talking about how to factor polynomials, and it's that you find the x-intercepts, also known as zeros. And yeah, I'm going to be talking about 5 methods to find this. Some are more useful than others. Under the right circumstances, all can be used. So firstly, I'm going to be talking about common factors. This is probably the most simple one. If each term in a polynomial has a common factor, this means that, let's say, AB plus AC is a polynomial, and AB and AC are the individual terms. And you can see that both AB and AC have A, so we can factor out A to get A times, in brackets, B plus C. This is pretty simple, so there isn't much left to say about it, except I'm going to give you an example. Let's say you get 6x squared plus 3x, and you can find that both of these terms have 3x in common. So you can factor this out, and then in brackets, you will be left with 2x plus 1. And next, this is my favorite one, just because of how much it can get used. It's called the sum product pattern, but a more easy way to remember it is the crisscross method, which I'm gonna talk to you about, and which will make more sense later. So you will get a polynomial that will look like this, just the standard form of a quadratic equation, which is ax squared plus bx plus c. And essentially, when factors of a multiply by factors of c get a sum of b, then this method will work. I know this sounds pretty intense and difficult, but with an example, this will make a lot more sense. So let's say you have the example 2x squared plus 14x plus 12. So firstly, we will find the factors of a and factors of c that can get a sum of b. So some factors of 2 would be 1 and 2, and then factors of 12 would be 6 and 2. And now you can see why it's called the crisscross method, is because when we have to multiply in a crisscross method. So we would have to multiply 1 times 2, not 1 times 6, and we have to multiply 2 times 6. So overall, we will get 12, and we'll also get 2, and we will add those 2 up, and then we'll get 12 plus 2 equals 14, which is B. So we know that this will work. And now we know the numbers. The reason that we put them in a crisscross type of scenario is because we will have to connect them vertically, so you don't have to go through another confusing process. So that means that we can factor it into 1x, so just x plus 6, you just go across, times 2x plus 2. So although I put 1 and 2 here, this is really just 1x and 2x, but we don't really need that to figure out if this works or not. So just keep in mind that this is actually 1x and 2x. Now I'm going to be talking about the grouping method. This is just to find the common factors within multiple sets of polynomials. Sometimes this can be a lot more easy. However, sometimes this can be very difficult, because if it's easy, you can see here, it'll already be set up perfectly for you in neat groups. But sometimes, like here, there's only 3 polynomials, so you can't really group them together. So let's talk about this example here, 2x squared plus 7x plus 3 equals 0, and make sure that this side is 0. You can split 7x into 6x and x, so you can see that we have 2 groups here. And this is essentially just the first method that we have, but just with more steps and just more polynomials. So you can see here, the common factor of this one is 2x, and the common factor of this one is just 1. But you have to make sure that what the result you get for both of these are the same, which is why this method is a lot more complicated and hard. Is because you have to make sure that once you go through these steps that you can get a common factor result, which is x plus 3 in this case. So if you do though, you can see that you can move 2x plus 1 together, so you have 2x plus 1 times x plus 3. So yeah, so therefore this one would also work. So now let's talk about polynomial patterns. For this slide, it's just some common patterns that you should keep in the back of your head. So when you see these types of patterns, you know how to automatically factor them. So let's see, a plus b squared. If you expand this, you will get a squared plus 2ab plus b squared. And if you just find any polynomial in this type of set, in this type of pattern, you know that you'll be able to shape it down to a plus b squared. And if you get a minus b squared, it's the exact same, except you have to remember that instead of a plus for 2ab, you get a minus 2ab. And lastly, we're going to be talking about a minus b times a plus b. This is probably the one that you have to keep in the back of your head the most, because a lot of times some polynomials seem as if they can't be factored because you have like an x squared and then just a normal number. But actually you can, sometimes it's just because you have a minus b times a plus b. So you'll get a squared plus minus b squared. And you can see that this time you don't have minus 2ab. And lastly, we're going to be talking about the quadratic formula. The reason that this isn't my favorite, although you can use this to in any polynomial without any like rules to find the available roots if there are any, is because that it takes a pretty long process, which is seen through this formula here. So you will have to use the standard form standard form of the quadratic, which is ax squared plus bx plus c equals 0. And you can just use this formula, which you'll have to memorize. However, if you just use it over and over again, it'll come to you naturally. It's x equals negative b plus or minus square root b squared minus 4ac all over 2a. And this x is just talking about the roots or the x-intercepts. So you can just plug these numbers into here and you'll find the roots. If there are two roots, one root will be used to find through using the plus sign. So this plus or minus means you'll have to use both. So one of them would be found using negative b plus the rest, and the other one you'll get negative b minus the rest. However, sometimes there's only one and sometimes there aren't any, which are some special cases. And that just summarizes a couple of ways to find the zeros or roots or the x-intercepts of these formulas.